get an understanding of the inversion of stereochemistry that occurs at the alkyl center that's being attacked. We're also going to talk about various sorts of alkyl halides and which ones are better, which ones participate better in SN2 reactions, what sort of nucleophiles are good. We'll talk maybe a little bit today about leaving groups, but perhaps more in a future lecture. And the reason all of this is so important is this is the first time where we really get complicated. There are many manifolds of chemistry that alkyl halides and other compounds bearing leaving groups like alkyl sulfonates can participate in. We've talked about SN2 reaction, SN1 reaction. I've already alluded to elimination reactions, E2 and E1 reactions, which we're going to be learning about more in Chapter 8. And so really getting an intimate understanding of all of the components, the alkyl halide, what's a good alkyl halide, the nucleophile, what's a good nucleophile, what basic properties rather than nucleophilic properties predominate is important. What I want to start with is the stereochemical course of the SN2 reaction. And in part, the problems that students have understanding this was really brought back to me by somebody at the end of last class who asked me whether I'd be talking about this or when I'd be talking about it. And I thought back and realized, yeah, people do have a lot of trouble understanding and visualizing what the inversion of stereochemistry is. So we're going to take our time and use a few pictures on this. All right. So we get inversion of stereochemistry at the sp3 center. And almost invariably, this is an issue that's going to come up with a secondary alkyl halide. Could come up with a primary one if you had a deuterium. In general, as I mentioned before, SN2 displacement doesn't occur at a tertiary center because of steric hindrance. So in general, we're talking about secondary center. Let's take a very specific example here. And I'll give us, as our example, S2-bromobutane. And the importance in this example is not going to be so much whether our center is R or S, but rather that the bromine is pointing back into the blackboard. And we're going to treat this with a nucleophile. We're going to use methane thiolate, CH3, S-. In general, sulfur-based nucleophiles are very good nucleophiles. They participate very effectively in SN2 reactions. What this means is if you mix a thiolate anion and an alkyl halide, typically they'll react right away, and there won't be so many other reactions like elimination reactions. So I've chosen methane thiolate. You'll sometimes see me writing a counterion because you always have a counterion present, so this would probably be sodium present. Sometimes you'll see me just focusing on a nucleophile. Both are the same reaction, it's just a question of what we're expressing. So the alkyl halide is an electrophile. It wants electrons. The methane thiolate is a nucleophile. It has a big polarizable cloud of electrons on sulfur that it's willing to share. Remember, halogens are more electronegative than carbon. So as a result, we have a partial negative charge on bromine, partial positive charge on carbon. In other words, the nucleophile wants to come in to that carbon. If I were to go ahead, I'll just show one lone pair of electrons. If I were to show this reaction, we'd have an attack. And what's a nucleophilic attack? We'd come in on the backside and pick the bromine out. What's important is we're coming in from behind. We're coming in at 180 degrees from behind the carbon-bromine bond. And the overall result is that we invert the stereochemistry at the center. In other words, the bromine was going back into the board, but the thiomethyl group in our product is coming out of the board. And if you want to be complete, we can write Br minus as our other product. As I've said before, organic chemists often forget about this or often don't write this because we sort of focus on the organic components. I want to try to represent the course of this reaction in 3 dimensions, and this is hard to see. And unfortunately, because your models basically have fixed bonds on them, this is the one thing that your molecular models are not good at demonstrating. So I'm going to draw this sort of side on, where here's the bromine, here's the carbon that's being attacked. Maybe I'll draw in the carbon explicitly. And I've just rotated the molecule around so that here's our ethyl group coming CH2, CH3, coming out of the blackboard. Let me tidy that up. CH2, CH3. And here's our methyl group going back into the blackboard. Now, our thiomethyl nucleophile, I'll write over here, CH3S-, is going to come in, and here's a lone pair. Of course, there are 3 lone pairs. It's going to come in opposite from the bromine, on the backside of the bromine. We call this a backside attack. As we move into the transition state, remember that's that species that only exists for a fleeting instant, the length of a vibration, a femtosecond. As we move into the transition state, the center carbon here is going to go from tetrahedral to trigonal bipyramidal. We're going to, for that one instant, that 1 × 10⁻15th second, be violating the rules of valence and sticking around in this unstable transition state, sticking 5 things around that carbon as bonds are making and breaking. And I'm going to represent this as trying to represent our carbon as planar, with the methyl group going back. So here's my best representation of getting a plane with the ethyl group coming out, the methyl group coming back, a partial bond to the thiomethyl group. So here's our thiomethyl group, CH3S, a partial bond to the bromine. The transition state is halfway, or partway, I should say, through this process. Part of our negative charge sits on sulfur. We have a partial anion here. We've started to form the bond. Part of our negative charge sits on bromine. We've started to break that bond. And here's the real kicker. As we pass through the transition state onto our product, now we're going to have the sulfur coming in from this side. So we've rehybridized our carbon. Here's our thiomethyl group. Here's our ethyl group. It's still pointing out of the board. Here's our methyl group. It's still going back into the board. And the overall result of this process, then, is inversion of stereochemistry at the sp3 center. This is really hard to see in 2 dimensions, because ultimately what needs to be happening is you need to be visualizing all this stuff on the blackboard. So I put together a little animation that gives us more of a 3-dimensional view here. Let's see if I can work this. Okay, I think what I'm going to do, I put this together in Pymol. It's up on that same site that I have other things for people who like to play around. To give us a better feel of the three-dimensionality of this structure, here's our alkyl bromide rocking around. To give us a better feel of the three-dimensionality, I'm going to rock the structure. Let me see if I can get a laser pointer here to perhaps point out what's happening. All right, so we've got our bromine going back into the page, the hydrogen coming out. Here's our stereocenter. And we're going to be bringing in our nucleophile, and it's coming in backside. Let me add our nucleophile, our thiomethyl group. So our thiomethyl group is coming in from the backside. It's going to form a bond by putting electron density into the carbon-bromine sigma star bond. If that's a big mouthful, don't worry about the details, but that's what a backside attack means. So it's going to be forming a bond. It's going to move in closer, and so I'll show it coming in closer. And now we're going to start to form a bond. We're going to start to go planar trigonal bipyramidal at the central carbon. Let me now take us to the transition state. So this is just about in the middle of the process. So now the sulfur has a partial bond, the dotted bond I've represented to the carbon. The bromine has a partial bond. Here's our trigonal bipyramidal carbon, and this is our ethyl group pointing out and our methyl group pointing back. As we continue through the reaction now, again, this is a vibration, my representation of a blink of an eye, a femtosecond of chemistry. Now we're starting to form our bond to the sulfur. We've started to break our bond to the bromine. Bromide is leaving. As we've completed our vibration, now we have our bond to the sulfur fully formed, and there's our bromide anion, and eventually the bromide anion basically will go away, float off in the solution. Thoughts or comments? Can you see how these structures relate to what we have on the blackboard? Let me stop this thing from rocking for a second, and I'll go back to our very original structure, and I'm going to rotate it so that we go to the same way that I was in the blackboard drawing. So here we are at this point in the process. The bromine is here. Here's our hydrogen. Our nucleophile is going to come in. Here's our thiomethyl group. It's coming in. It's getting closer. It's starting to overlap its electron cloud with the carbon bromine sigma star orbital that's projected out in this direction. We come in to the transition state. Here's our trigonal bipyramidal transition state that I've represented on the blackboard over here, as best as I can, representing 3 dimensions in 2 dimensions. Here you can see sort of how I've represented it with the ethyl group coming out, the methyl group going back. There's the ethyl group, there's the methyl group, here's the bromine, here's the thiomethyl group. And as we come through the reaction now, we start to break the bond to the bromine. We continue, the bond breaks. We form the new bond. And here we are at our product. And then if you look at my rotation on this, you'll see how we've gone from the sulfur, from the bromine pointing back in the original structure to the sulfur coming out in the final structure. Thoughts? Questions? Well, I'm not exactly sure what the textbook is doing, but let's think about it at this point. Here you are at the final state. All of our charge has moved to the bromine, our negative charge. Here we are at the starting state. All of our negative charge is on the sulfur. Halfway through, we have some of the negative charge on the sulfur, some of the negative charge on the bromine, half a bond, if you will, to the sulfur, half a bond to the bromine. And so we have half of our charge in each place. Now on top of this, remember what I said, that already we have a polarized bond. That the carbon-bromine bond is polarized such that carbon has a little bit of delta positive on it. Electronegative bromine has a little bit of delta negative. So superimposed on that, there's a little delta positive on the carbon, a little delta negative on the bromine. But those are dwarfed by the whole charge on the sulfur, the whole charge on the bromine at the end, and those partial charges halfway through. Other questions or thoughts? That's a good question, a very relevant question. How does the electron density go from sigma star to sigma? When you start to learn about orbitals, and particularly the Diels-Alder reaction and the Woodward-Hopkin rules, you will get a very babied down version of what's called conservation of orbital symmetry, which basically means all of your orbitals in the reaction transform through a continuous process to orbitals in the product. What that means is as this reaction is occurring, the carbon-bromine sigma bond is becoming the sigma star orbital of the product. And conversely, the sigma star orbital, the carbon-bromine sigma star orbital, is becoming the new sigma bond in combining with the sp3, roughly sp3, hybridized orbital on the sulfur. And basically what you can think of is that there are no electrons in the sigma star orbital, and we're taking and putting 2 electrons in them. And at the same time, there were electrons in the sigma orbital, and those electrons are going to bromine, and it's now becoming sigma star. Conceptually, that's a lot to grasp onto. It's largely beyond the sophomore level, so don't worry if you said, hey, that's confusing. But that's kind of the gist of what's happening. And it really is interesting. I mean, this is profound and this is powerful. And this actually gives us tremendous understanding of, for example, a stereochemical force of reactions, not just the SN2 reaction, but also reactions like the Diels-Alder reaction and electrocyclic ring opening and ring closing reactions, which we'll be learning about later in the sequence. Other questions? Let's take a look now at a couple of more examples. And I'm going to go through this process a little bit more quickly because I hope now we've been able to internalize this idea of inversion of stereochemistry. And so I'll just give us 2 cyclic examples. In some ways, cyclic examples are easier to understand because stereochemistry is staring you in the face. You can think of the front side of a ring and the back side of a ring. So let me start with trans 1-iodo-3-methyl cyclopentane. Just as an example so we can see our stereochemistry very clearly here. If I didn't have the methyl group here, this molecule would be achiral. It would be harder to see what's going on. And I'll take azide, N3-. N3- is another good nucleophile. It's a very delocalized, very spread out negative charge. We saw that when we were writing resonance structures of azide. Often nucleophiles in which the negative charge is spread out either by being on a big atom like sulfur, which is down in the periodic table, or by being delocalized. Often those are a little bit better nucleophiles and they take place take part in SN2 reactions a little bit better. So we'll take our azide, our N3-, and mix it with this secondary alkyl halide. And when we do, we undergo SN2 displacement. And the important thing is that we go from a trans stereochemistry to a cis stereochemistry. The azide comes in backside. Remember, we have our hydrogen over here. And so just as we saw it in our animation and just as we saw in our drawings, when the azide comes in behind and you go through your trigonal bipyramidal transition state, now the iodide is going to be pointing out of the blackboard. The azide is going to be straight behind the blackboard. In that transition state, hydrogen is lying in the plane of the blackboard. By the time we've gone through our transition state, now azide is behind, hydrogen is sticking out, very much in the same way that we had our inversion of stereochemistry here in the thiomethyl example with the bromobutane, and very much as we saw in the animation. So conversely, if I start with the cis stereoisomer, in which now I have the iodo group and the methyl group on the same side of the ring, and I treat this with azide, now we're going to go to the trans stereochemistry. Again, backside attack, inversion of stereochemistry. And I won't draw in the hydrogen here. I was just doing that to help you think about things. So thoughts or questions? Let's now talk a little bit about our electrophiles, our RX. And later on you'll learn that there are other things other than alkyl halides, but let's for starters just focus on alkyl halides in SN2 displacement reactions. Later on you'll learn about sulfonates and even epoxides that can participate. And the general principle is that good electrophiles are not sterically hindered. This principle is important. In an SN2 reaction, we have to transiently crowd 5 things around the carbon that's getting attacked. That's bad. In order that those 5 things can get in there, in order that the nucleophile can come in and get close enough to attack, we can't have a lot of steric crowding. This is one of the reasons for the principle that I said before, that in general, if you wanted a general rule, primary alkyl halides take part in SN2 displacement reactions. Tertiary alkyl halides only participate in SN1 displacement reactions. And I've sort of left secondary as a gray area that we're going to spend more time talking about. Obviously, I've just given you 2 examples with secondary alkyl halides. So we've got to get our nucleophile in. Some general rules of thumb that are so worthwhile, I always think of it as saying, all right, there are certain electrophiles that are just great in SN2 displacement reactions. Great electrophiles aren't sterically hindered. Sometimes there are little extra electronic properties helping them out. So for example, methyl halides. obviously the least sterically hindered you can get. There are 3 hydrogens on that carbon that's getting attacked. It's not like here where we had an ethyl group or a methyl group on it. Obviously, the easiest case for a nucleophile to get in close enough for that backside attack. There are a couple of others that are surprising, and the reasons have to do with the pi orbital on the allylic system participating. So all of the allylic halides are a little bit better than their corresponding counterparts. This double bond here manages to help steer in the nucleophile. The technical reasons involve interaction with the pi star orbital of the incoming nucleophile. But if you just want it as a principle, you can say these are extra good. Allyl halides are extra good. By good, I mean they participate fast and cleanly. And again, I'll say that since there are many competing reactions that can occur, like elimination reactions, this idea of one reaction being relatively fast is important, because if not, there'll be other pathways that you'll learn about, and those other pathways will give rise to different products. By the same token, benzylic halides are also particularly good. And really, as a point of general principle, I'm really talking about iodine, bromine, and chlorine. Fluorine really is not a very good leaving group. We're going to talk more about leaving groups and pKa's in a moment, but probably in our next lecture or so. But fluoride is kind of in a class by itself. And actually, and again, we'll talk more about it, iodide is actually better than bromide, and that's a little bit better than fluoride in these reactions. So if you're trying to do an SN2 displacement reaction, trying to avoid other side reactions, generally one wants to go with an iodide or perhaps a bromide. All right. So when I see methyl bromide or methyl iodide, I think great electrophile. There are plenty of ones that I think good electrophile in SN2 displacement reactions. So let's talk about some other examples. I would say good. What's good, what's not great, but eagerly participates in many SN2 displacement reactions, good alkyl halides, and again, I mean fluorides, bromides, and iodides primarily, are any primary RCH2X. The idea is, obviously, primary is going to have less steric hindrance than secondary, because you only have one group on that carbon where the nucleophile is coming in. Secondary, I'm going to call them fair. We just saw 2 examples with secondary, but it certainly sets up a red flag. Oh, other reactions might occur. It's hard now, by the time that you have 2 alkyl groups, I'll write it as R2CHX. By the time you have 2 alkyl groups on that carbon, it's hard for the nucleophile to get in as close. And so I set up a red flag that very often one might have elimination reactions competing. And I'm going to write, for the sake of simplicity in SN2 reactions, bad for tertiary. Tertiary alkyl halides can participate in SN1 reactions, but for the most part, with the exception of some intramolecular reactions, we don't see SN2 participation. So if you want this as a general rule, I'll put no SN2 displacement. What this means is it's too hard for the nucleophile to get in. Other reactions can occur instead. Now remember how we talked about anatomy of alkyl halides last lecture, and I really wanted us to spend a little time so we could see one thing from another. Let's come back to this, and I'm going to write it out explicitly, never at an sp2 center, just because there's such a myriad of compounds and myriad of reactivities that we see that it's easy for people to get confused. So I'll go ahead and deliberately write out a phenyl halide, and I'm going to put an X through it just as a big reminder. I'm going to write out a vinyl halide, and I'll put an X through it as a big reminder. You know, one other rule or principle, and this applies a lot with primary. This is a little harder to see. Beta branching and makes an SN2 reaction slower. What do I mean by beta branching? Let me show you what I mean. Let's take a propyl halide. So I'm going to write this generically as X, but if you prefer, we could have it as a bromide. We've already talked about the alpha center. I've already talked about, well, this is a primary center where my finger is pointing. If I put another carbon attached here, it would be a secondary center. If I attached a third carbon, it would be a tertiary center. This obviously, this position that I'm pointing at now, obviously doesn't affect whether it's primary or secondary. But it does make steric hindrance. So as we go from propyl bromide to isobutyl bromide, or propyl halide to an isobutyl halide, it gets harder for the nucleophile to get in. An SN2 reaction becomes slower. And by the time we put a third beta branch, by the time we get to a neopentyl halide, so I'll go from my propyl halide to a, I'll write it the same way here. So I'll go from a propyl halide and an isobutyl halide to a neopentyl halide, where now I've put 3 carbons on the beta position. That really makes it very hard for the nucleophile to get in. If you make a model of this with a tert-butyl group here, a neopentyl halide, you'll see it's very hard for the nucleophile to come in for a backside attack. No matter how you try to arrange your tert-butyl group here, it always ends up getting a little bit in the way. And so I'll draw a much greater sign just to show that the rate of SN2 displacement at a neopentyl halide is very slow. Let's take a look at a couple more examples just to help drive home some of the points on these last few Blackboard panels that we've been talking about. All right, let us take sodium methoxide counterion. As I said, you can pay attention to it, you can not pay attention to it. Sodium methoxide is the base that you would get if you took a very strong base with methanol, like sodium amide or sodium hydride, or if you took sodium metal and dissolved it in methanol, which would generate hydrogen gas and sodium methoxide. So let's take our sodium methoxide. I'll start with this halide, and I'm going to give us a specific example. Let's take this chloride. So I look at this and I say, this is a benzylic chloride. It's a great electrophile. This is the sort of compound that just loves to participate in an SN2 displacement reaction. Sodium methoxide is a nucleophile. The oxygen has lone pairs of electrons. It's willing to share those electrons. So it attacks. It does an SN2 displacement reaction. And the product of the reaction is the corresponding methyl ether. In fact, we call this a Williamson ether synthesis. And if I want to keep track of my byproducts, organic chemists don't always, I'll write out sodium chloride as the other byproduct of the reaction. Now, conversely, if I were to say, take my sodium methoxide and treat it with chlorobenzene, now I'd say, wait a second, that's not an electrophile. That doesn't like to participate in SN2 displacement reactions. Our chlorine is on an sp2 hybridized carbon. We don't get SN2 displacement in sp2 hybridized carbon. The bonds are too strong and you can't get the backside attack geometry. And so I'd write no reaction. Under some extreme conditions, with the right bases, other reactions can occur. But we'll learn about those later on in the class. But if I just mix them together, nothing's going to happen. If I heat the hell out of them, you might see some chemistry, but you'll learn about that later. All right, one more example just for us to see our comparison. And again, I'll use sodium methoxide. And this time, I'll take tert-butyl chloride. And you look at this, you say, oh, wait a second. This is a tertiary alkyl halide. So in spite of the fact that I might think that I could get an SN2 displacement reaction, that's not going to occur. Our nucleophile can't get in close enough to do its backside attack. It can't do the requisite SN2 displacement reaction. That doesn't mean there aren't reactions that occur. Reactions do, and as I said, in the next chapter, you'll be learning more about these reactions, elimination reactions. In fact, what one observes, I'll put this in parentheses for now just to say that you'll be learning more about it in the next chapter. What you end up is elimination to isobutylene plus methanol plus sodium chloride. And I'll just write out that this is an elimination reaction. All right. So I've been skirting around the issue of secondary alkyl halides. Let's now grab that issue. If I had to give you a general principle for secondary alkyl halides, it would be that with good nucleophiles, you'll get mostly SN2 displacement reaction. And with strong bases, you'll get mostly elimination reaction. By that I mean, if you mix a good nucleophile, like our thiomethyl sodium methane thiolate, you'll get, as we saw in the first example, mostly an SN2 displacement reaction. If you take a strong base like sodium methoxide, you'll get more alkene products and very little SN2 displacement products, but you'll have a mixture of products. So let's take that and write that out. I'll write out same compound. No point in showing the stereochemistry here, or just writing a generic reaction. Just for fun, rather than methane thiolate, I'll write out the sodium ethane thiolate. So the product of this reaction is going to be the thioethyl ether. And also, since I used the bromide, the sodium salt, we'll have sodium bromide. Conversely, if I take, instead of the sodium salt of ethane thiol, sodium ethane thiolate, if I go up in the periodic table, if I go to sodium ethoxide, now we have something that's much more basic. So I'll do the same reaction except with sodium ethoxide, CH3, CH2, O minus, Na+, what you get from throwing sodium ethanol or sodium metal or sodium hydride into ethanol. Now, we get mostly elimination. And by that I mean we get a mixture. And we'll be talking more about this in chapter 8. We get a mixture of trans-2-butene, cis-2-butene, 1-butene, and of course sodium. Of course we get, I'll write as the byproducts, ethanol, CH3, CH2OH, and sodium bromide. All right, let's see if we can make some sense of what constitutes a good nucleophile and what constitutes not such a good nucleophile. So we've talked a good bit about our alkyl halides. Now let's talk about the other component. So let's start by talking about what some common nucleophiles are, because part of what we do is just get experience here. So common nucleophiles well, the general property of nucleophiles, of course, are there's something with electrons. They want to share their electrons. They have electrons to share. So almost anything that's got a lone pair of electrons can be a nucleophile. Alkoxides, thiolates, we just saw both of these examples. Even halide can be a good nucleophile as well as a leaving group. We've seen in our previous classes, we saw cyanide as an example. Later on, you're going to learn about acetylide as an example. You may even have an example among the homework problems. I used azide, N3- as an example. You can also have even neutral compounds. You don't have to have charge. Sulfides, sulfur has a very nice large polarizable cloud of electrons, so they're sticking far out. It's willing to share them, even if it's not an anion. Also, alcohols under the right conditions, water under the right conditions. These particular nucleophiles often only react with really hot electrophiles like carbocations. Some general principles: more polarizable is better. And remember, better means reacts faster in an SN2 reaction, is less likely to participate in an elimination reaction. More polarizable means those electrons are spread out more. The atoms are bigger. The electrons move about more easily. So thiolate anion, for example, Rs-, like we've seen in our various examples, is more polarizable than oxygen that holds those electrons in close. It's easier to get in. Also means that sulfides and thiols and H2S are going to be better than ethers and alcohols and water, the oxygen analogs. All right, another general principle, and this can be a little confusing because we have to apply this idea in very analogous cases. And so I'm going to point this out, that we're really talking about basicity for one atom type. This is easy to confuse with the previous example, and that's for one atom type, I'm going to make a very big point. In other words, if we're comparing just oxygen or just sulfur or just nitrogen, more basic generally, because it can oppose steric hindrance, more basic generally leads to a better nucleophile. In other words, alkoxide is more basic than carboxylate, is more basic than alcohol. The pKa of the conjugate acid of an alkoxide of an alcohol is about 17, so alkoxide is more basic than, that's supposed to be carboxylate, O-. The pKa of the conjugate acid, carboxylic acid, it's about 4 or 5, so that's about 10 orders of magnitude, 13 orders of magnitude less basic. The pK of the conjugate acid of an alcohol, a protonated alcohol, is about -2, so that's not very basic at all. And the other general principle, and again, this is really comparing apples and apples, is less sterically hindered generally means a better nucleophile. So for example, methoxide, CH3O- is going to generally be a better nucleophile than tert-butoxide. Tert-butoxide with this big bulky tert-fuel group has the oxygen crowded it's very hard for it to get into that trigonal, to form that trigonal bipyramidal transition state. It's very hard for tert-butoxide to get close enough to an alkyl halide to do an SN2 displacement. It's less hard for methoxide. Later on, when we discuss elimination reactions, you'll see that this often means that tert-butoxide is used as a base to promote elimination, and methoxide might give rise to preferential SN2 displacement. All right, next time we're going to pick up discussing SN1 displacement reactions. We'll come back to some more examples of SN2 displacement reactions later.